This is lab 5, the falling slinky, and my name is Jack. The introduction, the lab setup included a slinky, a person to hold and release the slinky, a reference height like a ruler, and a camera to film it. However, I just used the suggested video and analyzed that instead, as I did not have a slinky at hand. The purpose of this experiment was to observe the motion of a slinky as it is dropped in a stretched position, so I can then compare the observed results with my computational model results to see how they differ and just analyze what happens to the slinky. This would be looking into the physics principles of Newton's second law, velocity and position update formulas, drag force, and slinky force as well. The observed video will be shown here, and some key observations to be made about this video is that the camera isn't moving, the object is only moving in one direction, the meter stick isn't shown as a size reference, but we know the distance from the mass to the fixed point by the height of the guy, and the system is the slinky, and the surroundings would include the earth, air resistance, the hand dropping or holding the slinky, and some drag force as well. Using the process I described earlier, I used the following tracker shown to the left to plot the position of the mass at each time step, to analyze and get data from the video, to use for both my observed and predicted models, which I will now further elaborate on. The code that I used will be shown here, and as you can see, some of the initial conditions I used were the mass of the slinky, the position of the slinky to start, and the drag constant for the slinky to make sure that I include drag. And then looking at the first for loop, you can see that the fnet is actually going to be 0. And this is the case because in the first phase of the slinky dropping, the bottom stays stationary while the top falls down first, because I analyzed it from the bottom of the slinky. And you can also see that I computed the forces of gravity downwards using F equals negative mg, as well as the force of the spring, which in this case is the negative of gravity, hence the fnet equal to 0. Then we use the position and velocity update formulas, Newton's second law, using the values we calculated earlier. And the same process applies for the second for loop as well, but instead in this case the fnet is not equal to 0, as gravity and drag are now working together once the top part of the slinky meets the bottom part. For the graph analysis, as you can see from the graph, it is clear that the expected results definitely differ slightly from the observed results, and this could be due to a couple things. One thing that could have caused this is the mismatch, or this mismatch is the way I track the position of the slinky, as I'm approximating the position of the mass where I thought it to be, but it could not be 100% right. And then there also could have been some fluctuations from external forces on the slinky that wasn't considered, or the slinky might not have been dropped perfectly straight. For this discussion questions, if you were to add weight to the bottom of the slinky, would it still fall the same way as we observed in the video? And the answer is attaching a weight to the bottom of the stretch slinky prevents the bottom from hovering because the added mass pulls downward immediately. The slinky's internal tension collapses faster and the whole system would begin falling together as soon as it's released. Only if the added weight is extremely small will the behavior look similar to a normal falling slinky like we've seen. And how does the bottom of the slinky stay stationary? The answer would be the bottom of the stretch slinky stays stationary because it is held up by the tension in the coils, which exactly balances its weight. And when the top is released, the loss of tension travels downward as a wave to the bottom, and the bottom does not yet know that the top has been let go. And until that wave reaches the bottom and removes the supporting tension, the bottom remains motionless. And for a conclusion, in this lab we observed that when a stretch slinky is dropped, the bottom stays motionless at first because the upward tension has not yet been removed. And using video analysis, we saw that a tension wave travels downward through the slinky before the lower coils start to fall to the ground. And this verdict was then supported by both the observed and tracked results, even though there was some slight variation between the two. And it was also, one of the lab was also just to look into the physics behind what happens and why it's a cool thing that the slinky falls the way it does.